It says recording, and then it starts counting up to 60.
Great.
Once.
Starts recording.
Starts recording. When you're done, you press.
Ready, go.
I'm Dan Shakimis, and my project is on calligraphy and lettering. So, just
Go ahead.
So the first thing that I did was basically these simple two-dimensional images of letters. I'll open the rest of them. Okay. So this is the first one I did, and it just, I mean, it's not just like a normal object. If you try and scale it, it will scale. And I'll show you the process. So it was basically a process of taking measurements from a box. So I used this letter, and I created a box around it, and I drew segments to parts of the letter, and then took a measurement of that, and then dilated the segment, and then drew, and then basically connected the dots. So that's why it scales. So I'll just let you see those.
So these are two-dimensional renderings
Yeah,
at
these are
this
just
point.
two-dimensional.
Okay.
This K. What I had to do was, actually, I think this is the first one I did. You get the idea. So, I basically had to create coordinates that they're missing, but I had to create coordinates that allowed for the points to connect and make the same size box that I did for the two-dimensional one, so that I could do the same process over again. So I basically found out what the coordinates had to be to make that size box, and then did that twice with a z coordinate to get distance in between them, and then I connected them. And basically I did the process of the two-dimensional thing twice over, and then just selected, like these are all just polygons here. Pharma. And should I explain this? Because this is
Very quickly, because
okay,
as I said, we
it's
have
basically
only...
there's x cubed plus y cubed equals z cubed, and there are no possible answers. And it makes this really crazy, like blender blade looking surface, as you can see with these, and I trace them. This is just my name, and then traced, and you can and it just like makes these really great images. This is an example of morphing. So you take the locus of a letter and then put it on a line to another one, and it like changes it, and it just gets these really funny looking things. And you can change its point in comparison to the origin, and it looks differently. So it's the word geometry on a sphere twice, but if you take it with the origin and you move, okay. Well, yeah, so it doesn't work for this one, but if you move the polygon, if you move the interior around, this will like turn into like a contact lens kind of shape, and you can change the distance and all sorts of things. And then I guess
There you go.
I'm Charlie Pastuzinski, and I did a project on non-Euclidean projections, meaning hyperbolic and spherical space. So I'm going to start off with the simple setup I made, and if I can just, well, right here what you see is the final product basically. This is a projection of a tessellation over a hyperbolic plane. As you can see, it kind of shifts in that saddle-like fashion here. But if we were actually to make this from scratch, let me just make this as big as I can. We'd first start off by showing all the objects here. I'm just going to delete these quickly. So we can start off creating basically any shape. Let's say we want a triangle to be projected, and we create the shape first, and then we can select the vertices and construct the interior of the polygon. Then selecting the polygon, we can do create a point on the triangle. This point is going to be very important because it basically acts as what's going to be projected. But it's the locus of it, which is the movement of where it's going to go, is going to be projected. So we select this and click measure abscissa and ordinate so we can get the x and y coordinates. So first we get our x, then our y here, and then there's the xy plotter tool here, pardon me, I have to get my z as well. And the z, you have to use an equation that you create for the radius of the little world you're creating, I guess you could say. So for example, for our hyperbolic space, it has to be the radius minus x squared minus y squared equals z. And z is the variable that's being defined here. And that's what comes from using that equation. What you did, I made a tool for that, but what you actually do is you click calculate, and then you can input square root, and then click 20 minus x squared minus y squared, and then you can do equals, there, you see you've got the z value there. So you're giving your z value, and then you can use the xy plotter tool here, xyz plotter tool. And that allows you to select 3 points, and you get this projection of this point right up here. And as you can see, as you move this around, it's going to move around as well. So you select the original point and then the point that's being created, and you construct a locus. And this actually creates a projection of the shape right there. So what you can do is you can move that around. As you can see, it cuts off a bit because you have to do the equation, basically the opposite version of the equation, to project it on the other side. Or, oh wait, that's only in spherical though, so it's actually working correctly here. And you can also approximately color these shapes by creating points on the locus. And if you create 3 here, you can basically approximate the shape by putting it on each of the vertices. So right here, and right here. And then if you click right there.
Which is, by the way, not advisable, right? You need to have a lot of them because it's a curved object.
Right, of course. But if we were trying to do this as simple as possible, we'd have to do create triangle interior. And as you can see, it looks really strange because of how it's projected. It's only projecting under there. So you'd have to do as many as you can around the curve. which makes it really hard to project these in a colorful way. So if we were going to return to the final product here, which was, let's see, here, we could also attempt to color here, but it's just very difficult because there's a lot of cutting off around the edges and colors don't overlap well. And as you can see, if you reveal what was the original, you can see that it's partially it's projected, and it's a pretty complex shape that's being put into this hyperbolic space. In addition to this, you can approximate other shapes. For example, let's look at this dove in hyperbolic. You see there's this, you start out with this picture of dove here, let's say, and you approximate it by putting shapes around the edge, and it can't be arrow selectable. You can turn that off by clicking in properties, arrow selectable is turned off. So you approximate that, hide the picture again, and you see you can actually move this little picture all over the place in the same fashion as we could on the other example. This is a, yes.
Yeah. Give it a spin. Actually, people
Okay.
may not realize what this is doing. So this is basically a 3D rendering,
Yep.
projection of the two-dimensional object. Yeah.
Okay. And chameleon,
OCA. Yeah.
and here it is.
Yeah. Give it a spin. Just
Okay.
physically give it a spin, so people can see it better.
And that's about that. And I have a few handouts. I can make some more, but I ran out of paper. I only have, I think, about 6 or 7. So.
I'm Lucas Frank. Okay. Okay, so I did some work in like navigation with ships, like how they calculate their longitude and latitude, and so like a pretty basic thing that's important for this, all right, well, so the North Star, if you look at the North Star from anywhere in the northern hemisphere and calculate that angle, it'll tell you your latitude. And the reason this works is because stars are much bigger than planets, and this is the sun, which is also a star, and then also because because it's very far away, and further something I'm not gonna show it, but gets away from it, like the more parallel these lines are going to come down to the Earth. So in the case of the North Star, the light rays are virtually parallel coming down to Earth, and also its true position is roughly on the Earth's axis of rotation. So that means if you're at the North Pole, it'll be pretty much directly above you. True position of where Polaris would be, but then its rays are coming down parallel. And then this measurement here is the actual latitude measurement, your north-south. And this measurement here is, right here, is what you would be measuring of Polaris, like from this is your horizon, and then you'd be looking up at the star. And as you can see, they stay the same because of these parallel lines and corresponding angles.
What happens if that point brought to the equator? Can you bring that point to the
Yeah.
equator?
So this is the equator, so if you're at the equator, the North Star will be at your horizon. And then if you're on the southern hemisphere, this doesn't work because you can't see the North Star. And then likewise, if you're at the North Pole, it's above you. Okay, and then longitude, well, so that's latitude. And then to calculate longitude, it was like a really big deal because no one had really found an accurate way of doing it in the 18th century. This guy figured out that so the Earth is roughly a circle, so that's 360 degrees, and then since it takes 24 hours for it to rotate around the sun, that means that each hour the Earth moves 15 degrees. So if you're on a ship and you manage to keep track of time where you start, and then at high noon you look at this timepiece, you can tell how many degrees away you are from where you started. And then this is just one of the three. This is the same thing Charlie and Danny did. It's a 3D rendering of the four corner states, which is like Utah, Colorado, Mexico, and another one, and Arizona. So pretty much it just shows how like, so the Earth is curved, so that's why like the sun will like keep moving around. It's kind of like a longitude kind of demonstration a little bit.
Yeah, hide the back bottom object, so yeah, so we can see that.
And then you can change like the curve of it, like change the circle size.
The curvature, beautiful.
And then I'm gonna have a class. So I measured the chapel to use a tool that measures angles, and so I'm just going to demonstrate like a trig function that like a proof of a trig function that we haven't really learned. So it's like triangles that there isn't a right angle. So you have a triangle. And then you just have the basic trig functions we have. So what you can do is draw an altitude down, so you have a right angle, and then the problem is to find the area of this triangle. What you do is you take sines of, for example, so area equals half base times height of a triangle, and then so what you do is so you take sine of angle C, and that equals opposite over adjacent, so that's H over A. And then so that equals H. And then also you take the sine of angle B, and that is H over C. And so that we have and so what this is saying is that the area of these triangles is going to equal the base, which is A. So this area of the triangle equals A, B sine of C, and that also equals AC sine of B. And if you divide both these by A, B, C, this cancels, and then you get what's known as the law of sines, which is essentially and then if you
Which one of us is taking the camera? It's a little confusing right in the middle, but it starts off slow.
Who is this? Who is this?
Alex Edelman.
That's it.
Alex
Okay.
Which one of us is taking the camera?
See this? This is a two-dimensional depiction of a four-dimensional object. That's 4 dimensions. A cube, which moves like us, is 3 dimensions. Now we think that Jordan is like this.
Okay. Hi, I'm Emily Cole.
And I'm Lily Pender.
So pretty much what we did was we figured out what the 4th dimension was, and then we made a movie about it, which is what you just saw the clip from.
And a synopsis of the film is sort of, so Emily plays a character who has been displaced from her original high school because there was a shooting at her high school, and she comes to Concord. and Anna, whose name is actually Anna Lubrowski in real life, is also a character who goes to Concord, and her and her friend Jamie, played by Tom Bloom, figure out that Jordan, which is Emily's character, was the one who committed the murder because she's from the fourth dimension, and therefore has the ability to pass through walls. Yeah. Do we have enough time to? Yeah.
Very quickly, yeah, totally.
So our process was very long. It started way back a while ago with both of us reading a book called Flatland by Edwin Abbott, which is basically this novel written by this guy about squares and triangles and what they do in their two-dimensional world and what happens when a three-dimensional character comes into it. And it helped us because it shows a lot about how somebody from a lower dimension tries to comprehend something from a higher dimension. And so that helped us when we tried to comprehend the fourth dimension. So after we read Flatland, we moved on to the fourth dimension. And that'd be a square, and that's a sphere. And the square is living in two dimensions.
Okay, so this is a three-dimensional sphere, and the gray area in this picture represents it's a two-dimensional plane, and it's sort of similar to the comparison in Flatland, which looked at the difference between the two-dimensional world and the three-dimensional world. And basically, we looked at what happens from the point of view of a two-dimensional person if a three-dimensional being were to intersect a two-dimensional plane, and tried to compare that to what would happen if a four-dimensional being were to enter a three-dimensional world. So this is the view from a three-dimensional sphere. This is what it would look like to us if a three-dimensional being crossed through a two-dimensional world. And it would just go through simply, and that's fairly comprehensible knowing since we understand.
But this is looking at it from the point of view of the square.
Can't find the points.
Well, we can explain it now.
Okay.
So pretty much the square would just see it as a small circle getting bigger and bigger and bigger and then getting smaller again. And if you put the sphere through. Okay, there we go.
Okay, so that's just a triangle, which is also two dimensions. That's not anything special. Right, this isn't working.
Well, that's pretty much what it would look like, though.
The fourth dimension?
That's here.
If a fourth dimensional object were to come into a three-dimensional plane,
It would just look like it was getting bigger and smaller.
it would look like a three-dimensional sphere getting really big and then getting really small.
Yeah.
So upon entering, it would get really big and then get really small when it was leaving. So similar to when a three-dimensional object enters a two-dimensional.
Are we?
And that, if you watch the movie, then we can actually show the entire demonstration and it makes a little bit more
Yeah, it
sense.
does.
Because it's not working right now. But squares, and you connect the corresponding points to create a cube. Does that make sense? With segments. And when you're creating a hypercube, you have two cubes, and you connect their corresponding points with segments. And it's just a cube to cube, if that makes sense.
Yeah. And we have a three-dimensional model you can see later. So.
Beautiful.
Hi, I'm Denise Samaras, and my project is called Dancing with the Star. It's basically, the process included making a prop which is known as the Great Dodecahedron, which is this thing right here. And the way that I made the prop was using a template that looks like this and enlarging it by 350% onto a bigger piece of poster board to make it out of sturdier material. And you basically have to like score or like cut along each each dash line in order to make the folds. And as you tape them together, as you see here, if you tape these two together, they become, like the star begins to form. And that's what it looks like complete, which is that. And these are some pictures of the dance you're gonna see. Basically with my dance, I used the song Soft by Lemon Jelly, and it's a modern dance. I collaborated with Alexis Newton, who made an animation, which is this thing in the background here. It's very colorful and it changes colors, so I used that as my background and I projected it onto a screen in the dance studio, which was projected on me. And we'll see a clip of the dance. Okay.
Enjoy it.
That's the projector, and then I'll just fast forward in. That's extremely fast forward, but if I pause it, okay, that's the animation, and as you see, it's changing colors, and that's my prop. And my inspiration came from the story The Little Prince, where he's kind of in this like other dimension where there's like nothing, and then he like finds a rose which grows in this other dimension. So that was, I sort of did like a play on with that and try to interact as much as possible with my star using the choreography. So yeah, and it's about a 5-minute piece, and everything was pre-choreographed until the day that I filmed it, when I used the animation. And that's what it looks like.
Oh, cool.
Hi, I'm Alexis, and I'm Alexis Newton. My project was basically to create a startup company, and I created a design on Sketchpad, which is this here,
Yay.
and it's here too. And I basically created it on Sketchpad and then got a company online to put it onto a t-shirt. And this is the t-shirt here. And on the back it says, Demo Day, Works in Progress. This is how I created it. I got my inspiration from a book called Sacred Geometry, and it's an Islamic design, and you can see it right here. This is a photocopy of the page in the book. And then this is how I did it. You basically use a bunch of different shapes, like triangles, and hexagons, and squares within each other. And then it had a lot to do with finding their midpoints. And then down here is, you can see, this design becomes that. And it's cool because it creates stars, but then it also creates more like abstract looking stars and other shapes. So it's a cool design. And then I worked with different color combinations to find what I liked best, what I thought would work best for the shirt. And I created this one, and then a more masculine design, which is here. And then here are some other, I don't know if you can see it, but here are some others that I tried out. But I like this one the best, so that's what I chose to use. And then in terms of the business and all of that, I collaborated with Denise, so that was sort of advertising for my company. And also Marjorie, in her project, did stained glass and used this design as one of her stained glass pieces. So, and then once I got this shirt, I ordered my own shirt first to make sure that it worked and everything, and then I had some friends model it and took photos of them. So this is one of the photographs, and I have a little catalog which I can pass around if you guys want to look at it. And then in terms of finances, I took orders from people. We posted something on the conference, which you probably saw. So some people ordered the shirts. A few ordered the girls, and a few ordered the boys. And I actually have some shirts to hand out to people in the class too. So Lindsay, you ordered one.
Yay.
So yeah. Here's one of your shirts. And then Eliza. There you go. And this is for Mr. Giselle.
Yay.
I'll leave that here.
Extra large.
Yeah, so in terms of paying for it all, I ordered my own. And then I worked with David Ross, who I used the school credit card to order the rest of them. Yeah. And then charged to people's accounts. So he got all the money back through Betty when she did all that processing. And then I also created business cards, which I can hand out to you all too. So I guess if you want to pass them down. And yeah, so that's pretty much the company. And I put a little step-by-step guide here.
If you'd like to order, call 1-800.
Yep, so.
Beautiful.
I'm Eliza Rosen, and my project is on geodesic domes. So to start off, I made a thing, something called the buckyball, which is a truncated icosahedron. So this is the buckyball, and it also, if like you haven't seen in chemistry, it also is the basic shape for a soccer ball. Oh, hold on. There you go. Yeah, so that's what the buckyball is. And there we go. So then I figured that I could, using the buckyball, I could make something geodesic. So I took the buckyball and I found the origin of it. And then from the origin, I found the centers of two of the pentagons that make up the faces. There's pentagons and hexagons. And then I made rays from the origin through the centers. And then I figured that if I drew segments, and then I put a point on each ray, as you can see going around, and I drew segments from the point to everything, so that's like what makes a geodesic dome. And just if you don't know what a geodesic dome is, it's like a man-made structure that is made in like a spherical shape, but it's made by like lots of triangles, and it gets like stronger as it increases, and it's like a really cool shape for a dome. So I figured I could do this, but it would be a lot of work to like do this for every single side. So with the help of another geometry student, Jennifer Enriquez, who was also studying the buckyball, I figured out that you could, the buckyball is an Archimedean solid, and that if I found the dual of it, I could find a geodesic dome. And a geodesic dome is a pentagous dodecahedron. So I took the buckyball and I found the centers of all of the sides. And then I drew to make a dual of something, every face becomes the vertices. So I made every face of vertices and drew segments connecting them. And then, I got a pentagous dodecahedron inside the buckyball. And then if I hide the buckyball, I have a geodesic dome right there.
Crazy.
As you can see.
This is a discovery. Like, it's a known fact, but these kids discovered it independently. Jennifer and like Eliza.
So, and then in terms of like where geodesic domes are in real life, I'm sure you guys have seen the Epcot Center in Florida, and that's a geodesic dome, and it's basically the exact same thing that I have on the computer, except every triangle is like triangulated like 90 times. like lots and lots and lots of times over to make it more spherical, and the more times that you like triangulate it, it gets more spherical. So, and like there's a lot of like famous ones that are like the Climatron Greenhouse, the Epcot Center, and the Montreal Biosphere. And basically the guy who created the buckyball, Richard Buckminster Fuller, created the geodesic dome, and he patented it in the U.S. and he like started domes, which I'll show something, which is like a way of people like living in geodesic domes, which is like a phenomenon. She wanted to become popular in the U.S., but isn't so popular now. But this is a picture of a dome home, which you can pass around if you want. You don't have to read the thing. And then this is a model of a geodesic dome that I made, which is basically like half of this, because I wouldn't be able to have it stand up. And yeah.
Beautiful. Go.
I am Ronan Marie Bozeman, and I created a solar system on GSP.
It looks like that. And over here, so it's based on our own solar system, there's no asteroid belt. And each of the orbits are kind of similar. The speed are kind of similar to their parallels in our solar system. And in a minute, a comet will come back around. And that's on a hyperbolic orbit. I'm not sure when it's going to show up though. So
Show the paths, maybe that will help
okay.
us.
So here are the paths of our system, and it's got 8 planets, 6 of which have moons. And they're on elliptical orbits, which I thought was kind of cool. And except for the moons, which are on circular orbits, and the comets on a hyperbolic orbit. And yeah.
Beautiful. So you had to learn how to do elliptical orbits, parabolic, hyperbolic.
Yeah, that was kind of difficult because you need to figure out how to make a locus.
Which one is her?
And then my
The third one. Do we really have
not
a
really.
like that?
Then my computer crashed, which was not fortunate. So yeah.
Okay, I'm Libby Chamberlain, and this is my project on geometric knots. And I examined knots in 3 different ways from a practical standpoint. So that includes like nautical knots and knots commonly used on boats, aesthetic knots, which are Celtic knots, and this also entails a little bit of research behind the knots and how they come into play in history. And then abstract knots, which are knots like the Mobius strip and the Bromian rings, which are knots that can't be undone. And they require a lot more research and kind of detailed examination of what makes a knot in a geometric sense versus what makes a knot in a practical, like day-to-day use sense, versus an aesthetic knot, what makes a knot beautiful to look at and kind of artistic. So yeah, I had a kind of an idea that I was going to have you guys learn how to tie some of these knots on the other end. And I pretty much that was the bulk of my presentation. And I don't know, what else would you like me to say?
Beautiful.
That's
Beautiful.
all I had in mind.
Yeah.
The Mobius strip is a one-sided loop. And I'll pass this around actually so you can play with it. It's a non-orientable knot, which means kind of along the same lines. We talked about this a while ago with topology and colorability, which means there's only one side to this, even though it's got twists in it. And you can cut it and it'll stay together, and it's really kind of fun to play around with and try to trace your fingers along. It actually shows up a lot in M.C. Escher's art. He's a big fan of the Mobius strip, and you can't really see it from here, but I've got 2 examples of how he uses the Mobius strip in The Parade of Ants, which is where you get the kind of adage that an ant could walk around the Mobius strip and walk along all sides of it because it only has one side and come back to right where it started. And then he also uses, almost tries to trick the viewer in the flight of swans because it's the same format, but as you notice carefully when you come closer to look, it's got two colors in it, so making it two colorable, therefore not a Mobius strip. So I'm gonna just pass this around.
I didn't understand.
Hi, I'm Lindsay College, and my project was about Penrose tiling. So I'm just going to give you like an introduction on Penrose tiling. So first, before you want to learn about Penrose tiling, you should learn about aperiodicity, which is aperiodic tiling is a tiling that never repeats itself exactly, so there are matching conditions and other local rules telling you how the tiles may be fitted together. So a great example of that is Penrose tiling. So it's discovered by this guy, Roger Penrose, in 1973. This is an example. It has no translational symmetry, so it never repeats itself exactly, but it does have five-fold rotational symmetry. So the pattern stretches infinitely, which you will see in a minute regarding inflation and deflation. So there are two popular variants of Penrose tiling, and one is made of kites and darts. So as you can see here, a kite is made up of sides with a partition 1 to phi and 1 to 1 over phi.
What is phi again?
Phi is 1 plus the square root of 5 over 2.
I.e.
The golden ratio.
Just in case.
Right, sorry. Golden ratio. So the dart is also partitioned like a kite, but in a different way, and they have specific angles, the kite and the dart, to make them unique. So the kite and the dart can fit together into each other, as you can see here, but they're forbidden to do so by the rules of Penrose tiling. So you can't fit in a kite and a dart together to make a full parallelogram. So in Penrose tiling, there are 7 vertex neighborhoods. So groups of kites and darts are on one vertex. This is the cartwheel pattern. So it's color coordinated with the vertex neighborhoods on your left, so they're easy to find within the pattern if you look closely. I have it on my poster outside, so you can take a look if you want. And you can see the sort of discolored area right here. That's just a decagon that you can find within Penrose tiling. So alone, you see the arcs that are where the kites and darts were partitioned from 1 to phi and 1 to 1 over phi, and they make a cool design that looks something like this. Other versions of kite and dart Penrose tiling are the star configuration here and the sub configuration. So inflation and deflation. So this is why Penrose tiling can expand infinitely. Deflation is a process that consists of several generations that you can see. So during one generation, each tile is systematically substituted by one or more new tiles that exactly cover the area of the original tile. So with the start of the sun, you can see if that happens. So here's an example that I did on Sketchpad you can see inflation. Another cool thing about kites and darts is that a kite and a dart fit exactly in a pentagon with its diagonals. So that's something cool about it, just an introduction. The other variant of Penrose tiling uses 2 rhombi with specific angles, pictured here. This is an example. Again, no 2 tiles can come together to form a single parallelogram. This is another example. This is an oil painting. So people like Schmid decided that this was really cool. So you can see the big and little rhombi if you look closely, tiling together. So where does this guy fit in? Kepler. So his tiling, which I created on Sketchpad here, was Penrose tiling. This was an inspiration for Penrose tiling. So this is just a little thing about what my actual project was. In 1619, Kepler realized that if 12 pentagrams, so you can see this pentagram in yellow, and then another one in green, and then another one in blue, just the stars, they go around. And if 5 pentagrams meet at each vertex, the resulting solid is this, which is called the small stellated dodecahedron.
So I built it with the surface of Kepler tiling, so it's sort of ironic because it's Kepler and Kepler. And yeah, so I made it by, there are 60 golden triangles with measures of 36 degrees and base angles of 72 degrees that come together on the pentagonal faces of the dodecahedron. So, that's
I'm Max Walsh, and for my project I did Cantor's theory of infinity, which Gregor Cantor was a German mathematician in the late 1800s, and he developed a series of theories on infinities and greater and lesser infinities, and whether or not they're infinities that are in fact greater or smaller. So it's mostly theorems and proofs and stuff like that. So there's really a lot to present. Part of my project also focused on fractals, which are these things, which are self-similar kind of shapes that have a pattern that iterates an infinite number of times within them. And this is one of the more famous ones. It's called Sierpinski's square. And so I'm just going to quickly explain probably Cantor's most famous proof, which is called the diagonal proof. And it proves that there are like infinities that exist that are greater than other ones. Basically that there are more numbers, any real numbers, which are fractions and repeating numbers like root 2 and pi and stuff like that, in between 0 and 1, than there are like the total number of whole positive numbers. And how we did that was something called the diagonal proof, which is basically the proof is if we're temporarily assume that someone has made a list of all the numbers between 0 and 1.
Can you state or write down the statement first so we know what the proof is going to be about? So what are you about to prove?
So numbers between 0 and 1 is greater than counting numbers.
Meaning the infinity involved with the real numbers between 0 and 1 is greater than
Yes.
the infinity of the counting numbers. They're both infinite, right? But he's going to prove that one infinity is greater than the other.
And how you do that is, so you temporarily assume that someone has made a list of all the numbers in between 0 and 1. And then, so so Lewis says like the first number is like 0, 0, 2, 9, 8, so whatever.
Dot, dot, dot.
Yeah.
Yeah.
So like that. And basically what you do is at the first number, you change the first decimal place to a different number. On the second number, you change the second decimal place to a different number. The third one, you change the third decimal place to a different number, and so on. So like at the nth number, you change the nth decimal place to a different number because they're all infinite fractions, or infinite decimals contained within this. And then you can always create a new number that isn't on the list, and that's how you do this.
Can you create one? Just create a number that is not on this list, for example.
So you would say like you change this to 1 at 6 and that to 7.
Dot, dot, dot.
Yeah.
Anybody gets it? This is like college level stuff, very, very profound. Do you understand why? So he's constructing a number that is not on the list. Yeah? Okay, very nice. And then, no, not yet. The fun part is coming, yeah?
Oh, the last thing I did for my project was make a conjecture about the Koch snowflake.
This is original Max Walsh. He has a conjecture of his own.
Which is that shape. Basically, it's triangles that just repeat on the outside of themselves and just build more triangles. And so for the creative component of my project, I made a conjecture about the infinity of the number of sides on the Koch snowflake, and Celine helped me prove that it was equal to the number of numbers in between 0 and 1.
It got two math teachers stalled for like a week. I mean, we were puzzled like crazy, very fascinating question, and at the end of this, we were able to come out. Okay? Beautiful original stuff. Very, very beautiful original stuff. Excellent. Thank you.
I am Tripp Clemens, and I study geometry and architecture. So for my project, I created a computer model of the chapel and like a 3D model of my house. So I'm going to show you a clip of the movie that I made about the 3D model of the chapel. Yeah, go for it. I'll talk a little bit about it after.
Dot plan of the scan that was taken immediately after the one on the left. Their overlapped result is on the bottom of the screen. Remember, we were technically only finding common dots between a cloud of billions. So, once we aligned all the scans together, the chapel fits seamlessly as one cohesive model.
Yeah, so you're going to see the model, and I'll explain to you how I did it. Briefly. That's the end of the movie, and the beginning sort of explains how I did it. Pretty much, I make an analogy. So a camera records light, like a machine called a scanner records the location of different dots. So there's this thing called a scanner. I'll show you. I can find a shot of it. Yeah, that's the scanner. And in the center of it, right there, it shoots out a laser, and it actually, from one scan position, it goes like in all 360 in 3 different planes. So after one scan, it takes about 6 minutes per scan. That laser will have seen everything around it. And when a laser hits something, it knows exactly how far away it is and where it is in relation to the objects around it. So my dad and I, this is my dad's equipment, he's a photographer, so he uses it for his business. We did a couple dozen scans from different sides of the chapel, and then we put them into a computer, and then afterwards you could mesh the different scans together by finding, okay, so you see that ball in the background, this thing? We placed like 30 of them around in the ground, like around the edge of the chapel. And after we had all the scans together, you could see these dots in the scans. And if there were 2 scans right next to each other, they could both see the same sphere. You could tell a computer, you could say, hey, scan number 1, you have the same sphere in common as scan number 2, and it finds these common points, and then it can mesh them together to create the final sort of
So this
model.
machine takes like a photograph of this?
It's a photograph, except that it knows. So in like a photograph, you have pixels. This takes a photograph, except it knows where each pixel is in space. Yeah.
And it merges them to make a 3D virtual model of the whole thing. Once it's finished, it basically becomes a rotatable object and so forth. What is the software you guys use? That final part?
It comes with the scanner. It's just Faro.
Of its own.
Software, yeah.
Its own. Okay. And your father is planning to still give an assembly?
Next year he's going to give an assembly. He might talk about this. I'm not sure. But he uses it for his business. He shoots cars mostly. He's a car photographer. And what this is useful for, so, traditionally people take pictures of cars by driving the car to the location, and sometimes that can be kind of difficult. Say you want to take a picture of a car in the desert or something. So what he can do, instead of bringing the car to the desert, he'll bring the scanner to the desert. Scan the desert, and then scan the car, and then just put it together. So it makes things easier. And it looks like totally real. The step after this, so I showed you guys we call it dot cloud. That thing, just the chapel, the final result of the model. That's like it's a dot cloud. The step after this would be to go around the sides of the chapel and take pictures of the different sort of textures, like the paint and the roof and the windows, and you can lay the textures on top of those dots to make it look like a pretty seamless model.
Questions? Okay, beautiful.